yes. So today what, please let me know, are you able to see the screen, anyone?
Yes, sir.
Okay. So today what we are going to study is, in the D drive, I'm going to take it. You all received the PPTs and the hands-on files, everyone?
Yes, sir.
Sir, to
Yes, sir.
hello, sir.
Yes, please.
Sir, to just a few minutes back, I received mail.
Few minutes back, yesterday itself I've sent you, yesterday evening I've sent you.
Yeah, but it is not loaded, sir. I got, I guess, some mail problem. But I have done this problem, but I'm facing in post processing, sir. Till solution calculation, till calculation, it is okay. But while post processing and monitoring things, I am getting problem there. I'm not understanding how to plot results and everything.
Okay. See, after if the same system, it was there in the same system what you are listening.
Yes, sir.
Okay, so after completion of this training, we'll discuss that. What you faced problem, we'll discuss that. Okay.
Okay, sir.
So
Yeah.
yeah. So what we are going to learn today is, I'll go with the chapter number 2. So here we have an example of turbulence model. Turbulence model in a Fluent. So what do you meaning of turbulence? The irregular movement of your particles, that may be fluid particles, that may be air particles, which is like turbulency. Okay, so that we are going to study it, and also we are going to plot it. Now here first I'll make you to understand this diagram. Here we have a pipe section. This you can take, the length you can take it, for example you can take length like 2 mm or 3 mm you can take, and dia is like 2.1 0.2 mm you can take for your example. Now this pipe section we are making air to pass inside this pipe section in order to calculate the turbulency, in order to calculate the skin friction coefficient, in order to calculate the outlet velocity. So this 3 to 4 parameters we are going to calculate. Now first we'll read the problem description, what they have given and what we are going to predict. So when I talk about the problem description or problem specifications, the inlet velocity is 1 meter per second, the air which is having 1 meter per second. The fluid exhaust into a ambient atmosphere, so out of the outlet into atmosphere, and density is 1 kg per meter cube, and coefficient of viscosity is 2 into 10 power of minus 5 kg per meter per second. The change of viscosity has taken us from a Reynolds number. Sir, what do you meaning of that Reynolds number? Yesterday I have given you the formula. So based upon that Reynolds number, how you define the Reynolds number? Re is defined as rho Vd. So I'll just make a note here. So you can just make a pointer. So how you define this Reynolds number? Re is defined as, Reynolds number is defined as rho V d by, I'm going to take coefficient of viscosity. So based upon this we can justify. There are different types of flows, but most of the cases we'll go with laminar flow, turbulent flow. Okay, so I'll be using this. Okay, so changing of viscosity is taken from the Reynolds number, which is 100 to 10,000. At the Reynolds number the flow is usually completely turbulent. So they have given the inputs. One is coefficient of viscosity, density and velocity they have given, and they also mentioned that is a turbulent flow. Now we will be solving this problem using Ansys Fluent. Among the results you will be look at what you are going to find it and what you are going to predict, what you are going to see in the post process. That we have, one is centerline velocity and skin friction coefficient, and also we are going to predict the axial velocity at the outlet. So these three important parameters we are also going to calculate. One is skin friction coefficient, centerline velocity, and axial velocity profile at the outlet. So now I'll give you a small logic in order to solve this problem. Okay, suppose Now you have a pipe section. Okay, we have a pipe section. Now what, we know that exactly at the center you have, the maximum flow will be there exactly at the center. We know that. What I am going to do is, in order to calculate exactly in the center of this pipe section, what I do is I'll be drawing only half of the portion. Now if you take this dia is, assume this dia is, for example, you take like 0.2 mm, you consider this 0.2 in terms of meter, you can take it. For example, you can mention this 0.2 meter. So what I'm going to do is, and the length, for example, I'm taking this as 8 meters, I'm going to take it. Now what I'm going to do is, out of this 0.2, I'm going to take only 0.1, because why, sir? Why you are taking this only 0.5? So in the settings, I'm going to mention that as a symmetry, because this bottom and both are equal. So what I do is I'll mention that as a symmetry. Now this I'm going to mention this is my center line. This whatever you have, the edge portion, I'll mention this as center line. Okay, instead of 2 mm, I'm going to draw only 0.1 mm. No, because why to calculate this? Please mute your voices. Now instead of 0.2 mm, I'm going to draw only 0.1 mm. So you can just draw only 0.1 mm. Then later you can know, and in the settings you have to mention this. Actually, original dia is 0.2 meters. Now what we are doing is, we will draw only 0.1. So in the settings, I'll mention this as a symmetric region. Okay, so that we are going to apply this logic. We are going to apply in the Fluent, right? So, and what are the rest of the things they have mentioned? So this inputs we are going to, the red color which I'm marking is this input parameters we are going to predict it. And the next you can see the dia is diameter of this is 0.2, length you can assume that as 8 meters, I'm going to take it here. And the turbulent flow exhibits small scale fluctuation in the time, within the time. It is usually not possible to resolve those fluctuations in CFD calculations, like what do you say, theoretical calculations. So the flow variables such as velocity, pressure, and etc. are time averaged. Unfortunately, the time average governing equations are not closed form. So they contain fluctuating quantities which need to be modeled using a turbulence model. No turbulence model is currently available that is valid for all types of flows, and it is necessary to choose a fine tune of model for practical cases of flow. Okay, there are like some other description, how to do the turbulence model and what equation we have to use it. They have mentioned here in this slide. What I'm going to do is I'm going to take the problem. So you can just start the workbench. Now we are solving that problem as 2D problem. Okay, so I'm going to take it here. You can take static structural. No, I'm going to take fluid flow fluent. So what the name you can give it, I'm going to give as turbulence flow. You can go with flow, you can take it here, turbulent flow, you can go it, you can take it this. Okay, now in the geometry, because we are doing a 2D analysis, right, I'm changing this property to 2D. The geometry analyze type, you can put it to 2D cases. I'm going to use 2D, right? So again, go to the geometry. So out of these 3 standard planes, I'm going to take XY plane. So units in terms of meters. So draw the sketch. As I told you, I'm not going to take full section. I'm going to draw only half of the section, rectangle. this, and dimensions you can mention this. Okay, this is of 8 meters and this is of 0.1 meter. So actually what it was given in this, it was mentioned as 0.2 dia, but I am taking only 0.1. So in the settings I will mention this as symmetry. So once concept surface from sketches, you can take it this and try to apply, generate it. Okay, so this surface you can change type to fluid, you can put it here. Okay, so that's we did it. Then you can save this project. Any question you can put it in the chat box, or you can unmute and you can talk to me. Please try to clarify your doubts. So here we have I'm going to do the default mesh, generate the mesh. I'm going to use it. I know that if I do this general mesh, I feel it is not good. So what I do is, because we know this top one is a pipe wall. Now fine mesh in the pipe wall, what happened due to viscosity, the flow will be opposing. So what I do is, I want to generate fine mesh in the top region. Okay, so what you do is insert, right click, insert, sizing. So in the go with edge filter, select the top edge and the bottom edge, you can select it and try to apply. So you can go with here number of divisions, that to 100 divisions. I'm going to use it. Okay, so how many divisions you can put it to 100 divisions. I'm going to use it there. So I'm going to use 100 divisions. So once we done it this, you can try to mesh it this. So behavior also you can give it hard behavior, exactly it has to follow. So next case is this could be the mesh. Now what again, now you can right click here, insert, sizing. So this, okay, and then you can try to apply here. So you can go with here. So here type, instead of element size, I'll go with number of divisions. So this time I'm going to give number of divisions to 30. I'm going to mention here. Okay, I'm going to mention the number of divisions to 30. I'm going to use, and behavior I'm going to use hard behavior, bias. So first cases, the bias factor of 10 should be increased. Now it's showing the bottom direction, right? So because we require in the top direction, because this is a center line. So change put it into other one. So you can put it in this, the second one you can use. So you see gradually it has been changing. Fine mesh is the top region. So behavior hard, and the next case is just try to fit to the screen of this area we required. Right click again, insert, sizing, this area, apply, number of divisions to 30, you can use it. So behavior, I'm going to use hard behavior, bias, I'm going to use 10 as a bias. Okay, so you can see now what happened exactly here in the top region, it is fine. So right click here and generate the mesh. Now if you look at this part, now here there is a irregular type. You see how irregular the mesh was there. So now to make this proper, right click here, insert, then you can go with the face meshing. So click on this face, apply and generate the mesh. Then you will get a proper order elements. Can you see that? Fine mesh will be there at the top region. Top region we have a fine mesh. can see the top you have fine mesh. Okay, so fine we have. So this way we have to do this. Now the ultimate thing is now I have to give the neighborhood selections. So how you're going to give the neighborhood selections? So that I'm going to go with edge filter again. So you can create a neighborhood selection because my system doesn't know, right, which is inlet and which is outlet. So create a neighborhood selections which is pipe wall. I'm going to use it here. Okay. And this is the bottom is I'm going to create a neighborhood selections that is of center line. Use it this. And this is our inlet. And this is our outlet. Okay, so one is pipe wall, another one is center line, inlet and outlet. So this way we have, so that we can do. So for future reference I'll be saving this. If it is no, if it is updating fine, it's not a problem, then you can go with future reference, export. So here you can take it. I'll take this as a turbulence mesh, turbulency flow. You can take this. Okay, then you can save it here, right? So then you can try to, or sometimes if it is no, what you can do is directly you can update here itself because already this file is open, right? Later we can update it. This is also one way you can do the thing. Now it is it's showing green tick mark. Later you can close those files. You can close these files, and this design file also you can close it here. Right, now then generally go to the Fluent applications. So go to the Fluent, I mean so already automatically it is taking dimensions 2D. I'll go with the double precision. Okay, so once we done, try to give OK. So just give OK. So now what you're going to do is, I'm not going to use scale or something because already we done this, units are in terms of mm. So now here you can go with checks, report quality, fine. So display, pressure based, absolute, steady state. Now I'm going to put it here axis symmetric. It is not a planar, right? So I'm changing this because we have drawn only point one. Now I'll put it to axis symmetric. Okay, so this is the setting you have to use it. So that have been used. So again model. So which model? Energy. Energy we require. Do we require energy? Did we are calculating temperature? No, we are not calculating. Viscous, K epsilon second equation. At the wall treatment I'm going to use it here. Okay, so this important things I'm going to use it here, right? So then go for here. They have given the some parameters, right, of air. They have given the inputs like velocity 1 kg per viscosity 2 into 10 power of. So they have given the inputs, so that we are going to use it here. So already we have air, so that I'm going to use it. So go with create or edit. So density, which is having 1 kg per meter cube, which is mentioned here. I'm going to use 1 kg per meter cube. Coefficient of viscosity, which is, so that I'm going to use, that is 2 e power minus 0.5. I'm going to use it. That change or create, you can do that, right? I'm being changing. Now go for cell zone conditions. So in the surface body, change type to air. Already air was there. Try to give OK. And in the boundary conditions, whatever we have defined the center line, no, that you can make this as a axis. Please do that as a axis. Okay, that we can put it to axis. Now the rest of the things, inlet, velocity inlet, outlet, pressure outlet, pipe wall, it will take that as a wall. Okay, one important thing is you have to change the center line. So inlet, which is how much velocity it has been traveling, which is traveling with 1 meter per second. So that I'm going to use it, inlet, edit. So you can go with your velocity of 1 meter per second we have. Now what is the dia of this, or dia of the tube? I'll go for intensity and hydraulic dia. So intensity is 5%, hydraulic dia is how much? How much we have the dia? So that is of 0.2 we have, right? That I'm going to use it here. 0.2 meters is the dia. That I'm going to use it here. Right? So those the important cases we know. Then you can save this. Right? So once we done it, so mesh is already we have not done, and rest of the things only inlet velocity they have given. No, rest of the things is they have not mentioned it. Inlet velocity is 1 meter per second, density is 1 kg per meter cube, viscosity is 2 into e power of minus 5. They have given the viscosity, that inputs have been applied. Now dynamic mesh reference values I'm not going to use it. And the next case is,
Hello.
here please.
Sir, what is reference value, sir, in Ansys there?
Which case? Reference.
Reference values
See,
was
you want to cross check, here it's showing reference values, right? You want to cross check it because in the boundary conditions we have given 1 meter per second. We all go there. So you want to cross check that. So go for here, inlet, you see, density is 1, and what is the velocity? 1 meter per second. You can cross check that.
Okay.
You know, right? You can cross check it that. So what inputs you have given, you can know inlet what you gave it here. So the parameters of here, 1k density is 1 kg per, so velocity is 1 meter per second. That's what we gave. Viscosity is 2 into e power of, that we gave it, right? You can cross check it that, right?
Okay.
So
Okay.
go to the solution methods. So I'm using here simple, and definitely we require turbulency, that second order. Yesterday I've told you why we require the second order and first order. So one element is going to split it into two elements, that is second order elements. Quad, if it is 4 noded, it is going to split it as 8 noded. When it's tria element, 3 noded is split it into 6 noded. So that way I'm going to use it. And movement is second order, turbulent we required, and turbulent displacement rate also I'm going to use it this. Okay, this important things I'm going to use it. Okay, so once we done it, again I'm going to save it this. Then so go for solution controls. I'm not going to change. So if you want to know, because usually these parameters, I'm not going to change this. Turbulent, which is required at 80%, dispersion rate is also. Monitors, now which area you want to predict the results, in which area you want to predict the results. So what I am going to do is I'm going for, so go for create. So what you can plot it, what you want to predict. I'll go for here, facet maximum, which area you want. I want to see the turbulency. Turbulency of what? Turbulent viscosity or turbulent dispersion rate, what you want to see. I'll take it turbulent viscosity ratio. I want to see that I want to change. You can change this as turbulency, so that whenever you're plotting you can see what the graph it was, so that we can easily identify turbulent viscosity ratio. Yes, I'm going to see that. Okay, so just try to, even you can write it that, try to give. Okay, now surface selected in the monitor, you can go for here, plot. I'll go with here turbulency. Okay, so face at maximum, so you can put it here turbulency. So turbulent viscous ratio, and which region, at the outlet or inlet, exactly at the center line I want to predict it, right? I want to predict at the center line the turbulency, right? So now I want to see any type of velocity. You can also create one more surface monitors, there you can provide it, right? So once we have given all the inputs, solutions, I'll go over here, standard initialization, I'm going to use it here. So standard initialization, from where you're going to take this standard initialization. So I'll take it from inlet cases. So you can cross check it that axial velocity is 1 meter per second, radial and turbulent dispersion rate. So radial velocity we don't have, radial velocity is 0. You can cross check it here. Axial velocity 1 meter. Just try to initialize this inputs. Okay, So now what I'm going to do is run the calculations. Yesterday I've told you what is meaning of this iterations. Okay, so this time I'm going to use number of iteration. For example, I go with 700 iterations. No sir, if you want 300 iterations, might be it can be solved of 250, it can be iterated. Now, for example, you can go with the safe side of 700. Might be you're going to be iterated 500 or 300 or 150, it is going to be iterated. Now this time I'm going for 700 iterations. So might be it can be iterated at 220 also, no? 220 or 230 it can be iterated. So once we done, try to calculate it. So you can just know which the turbulency or which region. This is at the axial way. The turbulency, you can see the turbulency at the axial region, how much it is having. So it is get converged. You see, you gave 92, but it is getting converged at 92. Okay, we cannot justify in that way, so it has got iterated over here. So then you can close this graphics, so counters, setup. So what you want to see that? So I want to see, for example, I want to see the turbulency or the pressure or velocity. You can see and try to display it. You can see how we have the velocity, how the velocity is getting changed. We can easily observe that. Or you can go with here turbulency, how the turbulence was happen. You can see, can you see that how it is getting changes. So you can see this how we have it, right? So you can see it. Now one thing, important thing is, now the post process, either you can see the results in the Fluent or the post process you can see in the Workbench also. No? What you do is, there is other quantity which important thing is, I want to find the one is center line velocity and skin friction coefficient and axial velocity. I want to see that at the outlet. So what I do is I want to plot as well as I want to see that. So files, you can go with data file quantities. So in that you can go with here other inputs. Already this input all be there in the counters, but some of the additional quantities in that you can go with skin friction coefficient. From there you can go with here skin friction coefficient. Yes, here we have no skin friction, just go with here. Okay, I'm just cross checking it. Sometimes it is not going to display. I'm going to use it again. Yes, so again you can save it, that file, save the project, right? So once we done it, then you can try to close it this. Now go to the post process of CFD. There we can plot the graph and all we can see there. Just put it in this Z plane. So what you can do is, so in order to plot the graph, definitely we required lines. Please put reminder, sir. Whenever you want to plot in the CFD post process, definitely we required lines. We have to create lines. So how we can create a line, sir? Now insert, sir. Without lines, can't we calculate using this edges or using they have surface, we have some edges, right? Using that, no, we cannot use by edges. Definitely we have to create a lines. We know that, right? We know that the total distance is 8 meters and from here to here is 0.1 meter. So we know all the points. We know x, this 0 comma 0, this is point is 0 comma 0, that is 0 comma 8, we can know that, and this point we can know 0 comma 1, 8 comma 0.1. You can know this 4 points, 1 2 3 4 points, we know that. So using that coordinate points we can easily create a lines. So how do we create? So lines. Okay, so what the line name? You can go with the line name. So I'm going to use pipe wall. I'm going to use it this pipe wall. I'm going to use pipe wall 1. I'm going to use, this top region is pipe wall, right? I'm going to create that. Okay, at which region? No, it is very easy. Like if you are good at in AutoCAD, like absolute coordinate system, now it will be very easy. Okay, so which region? That is 0. This is only 2. This is surface part, right? Only 2 coordinates, it doesn't have Z coordinate. So I'll go over here 0, 0.1, and this is 0. Another point is 8, and this is like 0.1, 0.1. Okay, so this way I'm going to create. So samples of 100 samples. What do you meaning of this samples? Like the line type, no, the line type you are giving 100 samples. Okay, we can, even if you give 10 samples, the appearance style will be different. It doesn't matter, the samples. So try to create it. If you see, there is a yellow color line, it is created there. Can you see that, guys? Yellow color line which is created there. Now the next case is, again we created the pipe wall. Again one more line I'm going to create it, line. So what line it was? So I'm going to give this pipe center line, pipe, you can go with pipe center line, pipe C line I'm going to use. C stands for center line, you can give it. I'm going to use center line, P C line. So which locations? This is like, if you want you can make a note, very easy, you can easily identify. Don't by heart it, just we know, this is your bottom is your center line, that is 0, 0 and 0, and this is 8 comma 0, 8 comma 0. Sir, what is meaning of 8? The total length of your section. So 8 0 comma 0, 8 comma 0 0, that I'm going to samples of 100. I'm going to create one more center line. See, one more center line, pipe center line is created there. Now, sir, why you are plotting? Again I'm saying, to plot the graph, definitely we have to create a lines. Okay, so then I'm going for here, locations, line. So what you want to know? Pipe outlet. So you can go with pipe outlet, I'm going to give it. Generally you can give the whole name, pipe outlet. You can go with outlet. So try to give okay. So that samples also 8 comma 0 0. This you can go with 8 comma 0 0, and this is like 8 0.1, 0.1. Now this one more line will be created over here, that is of 100 samples. I'm going to use it. So try to create it. Now can you see that? If you observe it, pipe outlet, you can observe it, right? So now we can plot it, the graph. So how do you can plot it? Sir, can't I show? Can you show the results? Yes, I'll show you the results. Then I'll plot the results. Go for counters. What do you want to plot? For example, I want to see the velocity counters. Velocity, you want to see that. You can go with the velocity at the center line or domain. You can go with here. So which region you want to see? I'll go with here this pressure. You can see how much it was having, 7.6 epo. That is, you want to change this type, you can go with here legend type, go with edit. So how you can go with appearance, you can change this type. So you can go with here, instead of scientific, you can go with fixed values. Try to apply that. How much we have? 0.7, which is having the maximum, minimum is 0.076, which is having there. Now what other things, you can go with the temperature also. Temperature, we doesn't have any temperature for that. No need, it will show the default. Okay, so you can go it here. I'm undoing this, the velocity. Now I want to plot it. Just try to put it here. So go with plot. How do you plot? Insert, then you can go with your chart, or directly you have a shortcut here. Now you can go with chart. So what chart name you want to give it here? So I'll go with wall y plus. I'm going to see that. Okay, so try to give okay. Now the title also you can go with wall y plus. Okay, just you can copy this, Control A, Control C, you can copy it. Data series also, the name itself, wall y plus. Location, at which locations? I'll go with pipe wall. Pipe wall, you can go with that. So in the x axis, what you want to plot? So I'll go with here in the x location. You can go with here. You can go with x as variable as x. I'm going to take it here, and y variable, what you're going to take is, I'm going to take y plus. Y plus, I'm going to, you can plot it that. Okay, so how we have wall thing. This is one graph. Again I'll go with here one more chart. Okay, so this time what you're going to plot it, sir? So I want to plot it the other cases like
Sir, excuse me, sir.
please.
Sir, why we actually calculate the wall y plus and what does it
See,
means? Wall y
wall
plus.
y place in the sense over this region, how the friction or the turbulence is happening at this region, at the walls region, pipe wall, how the turbulence was there. Now to calculate this wall, what is y plus? Y plus in the sense the turbulence at that region, at the pipe wall region. We have given for no. You can see this in the top region, pipe wall region. Pipe wall is in the top pipe now. At that cases, what is the turbulence which was there over there? That we are plotting there. Okay, understood?
Okay. Okay, sir.
So then you can go with here one more chart. I'm going to create it. So this time I want to see the center line velocity. So what you can do is you can go with center line velocity. Okay, just Control A, Control C. You can copy it every time. You cannot, title is also center line velocity. Data series also center line velocity. Okay, so then you can go with x variable. What you want to do it? I'll go with x variable as x. I'm going to take it, and y variable I'll go with initial velocity. Velocity u you can take it. Velocity u you can take it. Okay, velocity u. So try to apply it. So the data series location is missing because we have not applied, right? So yes,
Hello.
please. Yes.
Sir, what is velocity u in which direction?
See, what is the symbol usually when you calculating u stands for velocity, right? Velocity u.
Okay.
Okay, so at which region? Location I'm going to give pipe center line. I'm going to give the location. So this is the thing we have not given. So location is pipe center line. So x variable is x variable, y variable is velocity u. Usually we know whenever you calculating velocity, a symbol which indicate with u value. So that I'm trying to apply it. You see how the velocity has been changing. So which is having 1 meter per second, then how it has been changing from, I hope from 2.1. So from 2.1 there is a constant velocity you have there up to 8 meters. The total pipe length is 8 meters, right? You can see how we have center line velocity and velocity we have, right? So then what is the outlet velocity, or you can go with the screen friction coefficient. What is the friction over there that I want to calculate? So again you can plot it. So you can go with here chart. What you want to do it? I'll go with skin friction. Control A, Control C. So then I'll go with here Control V again. Data series. This is also location. Control V you can use it. Location which region? So that I'm going to use it. Which region we can go? Pipe wall, no, the top wall we want to see that. So x variable I'm going to take as x axis, and y variable you can take skin friction. No, see, suppose you are not updating there. What we did is I went for file other quantities, right? If you're not selecting there, the skin friction will not be displayed here. So try to definitely file other quantities, you go there and you select that. When you select in the Fluent, then only it will be visible here. If you're not visible in that, again this will be a problem. Okay, click on that. So try to apply that. So how the friction value was there in the pipe wall? So from the initially it was like 0.027 you have, then how the friction is changing at this up to, I hope from 2 meters the screen friction was constant 0.007. I hope we have exactly over there. Okay, so this we can, right? So this is one cases. Now I want to see the velocity at the outlet velocity. I want to see that. So go with here chart, right? So outlet velocity. Outlet velocity, Control A, Control C. So you can title, I'll put it your Control V. Data series also I'll put it to Control V. At what location? At the pipe outlet. So x-axis, what you're going to do is I'm going to use this velocity u. Now I'm going to take it velocity u. y-axis I'm going to take is y. Okay, so that I'm going to use it. So once you know, try to plot it. Sir, what happen if you make wrong? The graph will be opposite in the direction. No, you can do that in that way. So initially it was, we gave is 0.1 meter per second, right? So why 0.1? How the velocity? Up to it is gradually decreasing. You can see the velocity is gradually decreasing up to here, up to, so it is having 1.2 meter per second. Okay, so this is in terms of meters. You can put it in terms of meters this, and velocity here also you can change it. It depends upon you how you want to plot it. Okay, so this way you can plot it. Yes, any doubts till now? Any queries, any questions you want to ask?
Yeah,
Please
sir.
ask me.
Yeah, sir.
Any queries? It's fine.
Yeah, sir.
Okay. Gokul, Anurag, Ranjit.
Sir,
So voice is audible, sir?
Yes, yes, I can hear you. I can hear you.
Yeah, sir. Sir, I have one
what
doubt,
can-
sir.
Yes, anyone? Yes, Shanwas.
Yes, sir. It's deviations for its color variations is mainly correct, sir. Deviation is mainly for color variations.
Color variation, what do you meaning of that? I didn't understood.
Yes, sir. If you have some origin, if zero is origin, and then
Mm-hmm.
8 meters to its final. It's final. It's for some pipe or end line. I
Mm-hmm.
have for if middle if 4 meters, we have
Mm-hmm.
how to indicate the for velocity and how to compare for that calculations and how to if we have to if engineer terms we have some cut the sections for in 4 meters. We have to some what velocity have like in 4 meters likewise.
At least
So
one thing I didn't understood what you're trying to say me.
yes, sir. If this graph and these comparisons for if all variations,
Mm-hmm.
we have some individual variations. We have middle for 4 meters, what velocity we having and what
No, you
mass we.
want to check it for 0 point. No, you can see it, right? See, usually you can compare. No, either you want to export to Excel sheet, you can also export to Excel sheet also. See,
Oh,
now you
see,
can see export here, export to current sheet. No, you can export it. What? No, you can see CSV file. Then you can put it to computer document. For example, you can take it Fluent. Like what you want to see it. Outlet velocity. Already we was there. Outlet velocity. Try to save it there. Okay. So what you can do is then you can see that how much velocity it was there. You can cross check that.
okay, sir. Okay.
You understood now?
Yeah, yeah.
Outlet velocity. Then you can see 4 meters, 3 meters. You see here the velocity. Like now you can see it there. Suppose you want to see at the 4 meters. Now this is at 9.1, 9.1. All we have it here. It is showing no that this is no a velocity no in terms of meters no 4.4 meters. How much velocity? 1.2 we have there. Or you can right click here. Then you can change this type. Sort by decimals of. You can put it here. How you want to give it, you can go with your decimals. Fill and all you can put it here. How you want a general way.
So can we view the results in 3D?
View results in the 3D. What do you mean that?
So actually we designed this model in 2D and assigning the boundary condition that is as axis symmetric, right?
Yes, yes.
Can I revolve this model in 360 and analyze the flow of the fluid in terms of streamlines?
Yes, why not? Here also we can see the streamlines, right? Here also we can see the
But in
streamline.
2D, so volume render, which is related to
Yes,
like
we
this.
can do that. We can do that.
Yeah.
Okay, volume render for 3D, you can do it here. You have no volume render, you can do that.
So we can apply for 3D, sir, but right now we only have the 2D model, right?
Yes, we can do that. 3D we can do it, but 2D it will consume more time. That's the reason I have explained in terms of 2D.
Okay, sir, and also in that general condition, we chooses that axis symmetric one. So the one more option is in the below axis symmetric and some other like spiral
Spheral
or
option will be there. Axis
yeah.
symmetric spheral option will be there. If it is a rotational object, then we have to specify there. Now it is a planar, right? See, our section
Okay.
is like planar. Generally, how
Okay.
you have, we
Mm.
have, see now this is like, we have one pipe section. This is a planar cases. So suppose if we like revolve in the features, then we have to go with spheral option. If a object is in terms of revolved cases like this in the revolved form, okay, revolved form,
Okay.
then we have to use axis symmetric spheral option.
Okay, fine.
Suppose you take a revolve feature of a bottle, you take bottle, that is a revolve feature. Okay, so that time you can take that as spheral, axis symmetric spheral. Okay, suppose you take this is a revolve feature. Now what you do is, now if you cut it into 4 equal parts, you know that is a symmetric. See, out of this, in order to complete your job very fast, instead of solving for all 4 coordinates, I'll take only this portion up to from here to here I'll be taking.
Okay, when I choose fill option, so
So
how
it is
can I
going
assign
to,
that act?
yes, it is going to assume this with respect to this axis, we are going to assume that.
Okay.
It is going to assume that this is the axis. Now it will take a revolve spheral option.
Okay, sir. So, and also I'll try to search for that wall y plus. So just now, and it says that it's a dimensionless wall distance, but anyways, it's not related to anything turbulence. So I just a little bit confused about that term. So why we actually calculate
No.
the
See,
wall y plus?
wall y plus in the sense, see,
Okay.
with respect to the part, whatever you do the part. Now I want to calculate the top region, the turbulence at the top region. I want to calculate. So you can calculate there. So they have different names. They'll see. I want to calculate y plus. They for every writer they'll put it their way. See, wall y plus, wall my y minus. Suppose you take this is a coordinate. Okay, x coordinate and y coordinate. So
Okay.
y positive direction, y negative direction. This y x positive direction, x negative direction. So that's the reason I have to over this in the top region. Okay.
Okay.
No, sir, I don't
Fine,
want to
sir.
have wall y plus. Then you can you can undo that. Not a problem. So our ultimate thing is I want to calculate the center line velocity. One is screen friction coefficient and one is outlet velocity. These 3 are important parameters I have been calculated.
Okay, sir.
Okay. So next, yeah. Any queries?
Sir, one question.
Yeah, please.
Sir, how to generate report for this analysis?
Report. Oh, here we can have here itself. We do have that. A report. You can see a report previewer. You can find it that whole report. You can see, right? Even if you develop a graph, so everything it will be saved here. File report, mesh report. You will have all this. Okay, then you can go with publish. So in which format you want to? I'll go with the text or PDF. So save images in the separate folder. You can save it. You can go with generate a CFD viewer. We can go with here. How you want to save it will save it as HTML. Go with the text. Okay.
Sir, what if we want to add any images to this report?
You see here I have not added image. Now you can want to add, just click on this velocity also. So then again you can try to generate it again, report previewer. Definitely it will be going to add it. So you can take it here, figure. I'll go with your 3D view. You can add an image. So you can add this image. Right, it is going to add. Again you can go with the report preview. It will be added. I hope. It is not updated, but you can just refresh it. Okay.
Sir, one more doubt. Sir, is it possible to simulate like how the velocity flow?
Simulate. Okay, now you can go with here 3D previewer. So then mostly if you want to generate animation, no, then you can go with streamlines. Streamlines will be having. If you go with counter and other thing, it is not going to play animation. So you put as velocity. You can put it here. Okay. Velocity is already there. Then you can put it here 1 2 1. Okay. So then here starting from velocity inlet. I mean pipe outlet, pipe wall, inlet, yes, this is inlet cases. Try to apply it. Okay, then you can go with counters, velocity 1 to 1. Just go with slow speed. You can try to play it. So you decrease the distance between that the balls and all. Right, you can stop it.
Sir, one more dot. How to save this animation? Yeah.
Yesterday I told just I will stop it this. So here options, save this movie, it was there, right? Can you see that? Just enable
Yes.
that.
Yes, sir.
And you locate the folder where you want. Let it get stopped. Again go for here movie, save this movie, which location, you can put it the folder. Just go with save it there, cancel. So automatically once you play it, then it will record the whole thing and it will be saving there. Okay, so you can change this options, then you can change this ball size and all. You can put it here. Then I'll want to save this. You can go here. Repeat forever cannot be combined with save movie. Here only one loop I want to save it. So you can see it is getting saved. Let it get saved. Now what is your task is what you want to complete here. See now here what I did is in this section, so I went for 30 divisions, right? 30 divisions I made here. See, okay, so this sections here, if I draw this, I made here 30 divisions. 30 divisions over here, 30 divisions I made here, 30 divisions. Now what you have to do is you have to put it to 60 divisions. First you solve with 30 divisions, then you have to change to 60 divisions, and top is also 100 divisions I gave, 100 divisions I gave. The bottom also 100 divisions I have given, has been split into 100 divisions. Now you have to change this 30 to 60 and you see the changing. What is the velocity, how it is changing, how the skin friction is getting changes, and the wall y place is getting changed. So that important, even including central velocity also, how it is getting changes, that you have to discuss. Understood?
Yes, sir.
You can just I hope.
Excuse me, sir.
Yes, please.
Suppose, sir, if I want to find the failure, so sir, what kind of parameter can fail in this case?
What can you repeat the question again?
I want to know, sir, which kind of parameter will fail in case of Fluent?
Which kind of parameter
Will failure in case of Fluent?
What you want to see? Which kind of parameter, in the sense what parameter? Failure matlab what do you want to calculate?
Sir, when I was learning static structure, whatever on there, I'll check if I'll impose such kind of load, then material will fail. So can I check fail or not in this case?
No. That failure you cannot check it. You see where is the maximum, how much velocity it has been having, that you can check it. Here you cannot see the failure. That is deals about solid body, you deals about deformation, stresses, factor safety, you do it. But here you study about how much velocity, what is the temperature developed, is that in the stable stage or not. We have to check it that.
Okay. Sir,
Okay.
another question, sir. Sir, when I'll check the velocity, then in x-axis I'll apply velocity u, and y-axis I'll apply y only. Sir, why?
You want to change, you can change it. See, it doesn't matter that only you have to apply in that way. Whatever I did it, you want to do it in that way. It doesn't matter like that.
Okay.
No, it doesn't matter like you have to apply only in the x direction. What happened? This x will move here, and then a graph will be in the reverse direction. It doesn't mean that you have to apply in the x direction. No, you can put it this x also in the y, and this y plus also in this direction. You can also put it that. Okay.
Yes, sir.
Yes. Any queries? No queries. Is that clear? No. So you are
Yes,
clear
sir.
with the task what I gave. The second task what I gave you. You are clear with that.
Sir, if I have any for given for tolerance, we have to some velocity if 0 to for 1 so it's okay means we have to some tolerance given the nominal values.
Tolerance.
Yes, sir. If given some tolerance, it has been its nominal values.
Mm-hmm.
Okay. That values is given that any for a simulation side or a graph side to report.
I didn't understand, man. What tolerance you want to give
Yeah.
to
If have
which?
any sir, if velocity it's 0 to it's 1, it's okay. If above it's 1 or it's not found. It's some for we have to some.
Conference.
Shanvas, I'm not able to understand what you are asking me. What tolerance you want to give in the sense?
The sense mean not sir. If nominal value sir, if 0 to if 1 velocity it's okay. It's above it means we have to not okay with that.
No, you
So
want to justify that. See,
yeah.
once it is like 1 meter per second, here we can check it. We doesn't say that if it is like more than 5 meter per second, it is going to break, or we cannot justify that way. See here how when it is 1 meter per second, how the fluid is passing, that you can check it here.
Oh, okay.
Okay. So if it is like temperature is more than 40 degrees, how the temperature you can see by seeing the counters where it is getting reacted more deformation or more temperature was developed, you can just see there. Okay.
Yeah, it's okay, fine.
Okay. So you are clear with the task what I gave, I hope. Yes, Santosh.
Hello, sir. If you want to check like stresses due to pressure or temperature, again we need to perform couple field.
Yes.
Okay. So couple field analysis we need to perform. There
We have
again
to go
we
with
need
we have to go with the same results to the other application. I mean other module.
structural analysis. I'll take and I take these results as a load,
Yes, yes,
like we do in temperature stresses.
yes,
Sir,
yes.
is it possible to combine that CFD Fluent to the static structural workbench?
You want to compare, yes, because both are same. No, you can take this results to the other applications.
No, sir. He is asking about like due to the pressure change, what will be the stress result, right? So can
Yes,
I
yes.
combine the static structural to the Fluent flow?
That I was not clear, man. I have to check with that because I have not tried it.
Okay, sir. So is there is any module to edit the mesh in Fluent itself? So if I have any mesh failures like Jacobian and aspect ratio like that,
No,
so I
no.
want to modify the mesh.
Elements you cannot control, but you can decrease that because each and every element you cannot edit it.
Okay, in hypermesh itself we can edit that mesh, but here we can't.
Here we can change it.
Okay, right.
Okay. Clear, no?
Yes, sir. Fine.
Okay. Okay then. So yeah. So we'll see with new topic. Please do practice. I'll be there in the online itself. Come back with the doubts. okay, and send to my mail ID.
Thank you, sir.
Okay, then
Don't have your mail ID, sir.
in the chat box again I'll send you that. You can just go with that. Tech support dot cae2@iidesign.co.in.
Sir,
Okay,
it is good if we get mobile number also.
mobile number. Sure, I'll
Yeah.
do that.
Please. Thank you, sir.
Okay, you can take this.
Thank you, sir.
Yes.